Next topic is recursive definitions. Now we're not going to do that much about it. So only the first few pages into this section we'll talk about. We're going to do much more about recursive relations and recursive functions later in a later chapter in the next month or so. So this is more of an introduction to the topic. Okay, so but it is related to induction and strong induction, so that's why we want to mention it here. And so what is recursion? I mean, many of you are familiar with computer science and know that recursion is something that is often technique that is used. It's extremely useful because it allows you to do define something without going back all the way to, if you want to find something for 100, you don't have to go back all the way to 0 to build it up. You build it up step by step. So it's very similar to induction-like kind of thing. It's like going one step at a time. Okay, and so let's give an example of a recursive definition. So this is about functions. So the recursive definition of functions. And this is a little bit general. So in general, we're talking about a function from the natural numbers to the natural numbers, from the integers to the integers. From, let's say, integers. Remember, that's how we denote integers. Or from the real numbers to the real numbers, or from the rational numbers to the rational numbers. We are a little bit vague in what we mean with a function here. It depends, you'll see immediately from the context. By the way, it doesn't have to be numbers. It could also be strings or other stuff, but okay. So, now, as in induction, there are again two parts. There's a basis step, and there is a recursive of inductive step. But in this setting we use the word recursive, but it really means almost the same as inductive. It's a recursive step. So here's an example. A basis step will mean this is the value of this function at the beginning. Now, the beginning, we have talked about this very much. This could be at any given time, right? Sorry, I realized I made a little bit of a mistake here. Sorry. Let me back up what I said here. What I meant to say are these are functions that take values in integers or values into the real numbers, but they're indexed by natural numbers. I'm sorry, it's always indexed by natural numbers. So in the basic step, we start with, normally they start from 0, but they can sometimes start from 1 or 2 or 3. We have now been familiar with this, but let's assume that we start from 0 and we say f0 is equal to 3. So that's if you want a definition. We say f0 is equal to 3. We're defining this function, and then we say, and then the next step is the next value of the function is obtained by taking twice the previous value and add 3 to that. Okay, that's an example of a recursive definition. Now, for which n is this? For all n at least 0. Okay. Let's first work out that this works. I'm going to change this in a sec in my notation. It's just a notational change, but for now, let's try to figure out what this means. Suppose I want to know what is f of 4, right? If this is if I'm claiming that this function is well defined, I will discuss a bit more what that means. But I'm now saying this function is well defined, so it means I can figure out what f4 is. How do you do that? Well, this tells me you go to the previous value, right? This is how you have to interpret this. The next value is given in terms of the previous value. So therefore, we, instead of writing it this way, we will more often, so in induction you go from n to n plus 1, but mathematicians often set the induction up the different way. It doesn't matter what you write n and go into the next one n plus 1, or you start from n minus 1 and the next one would then be n. And that is sometimes neater, it's cleaner to do. So that's what I'm going to do here. So I'm going to define this again, the same definition, but say the value of n is obtained from taking twice the previous value and now subtract 1 from it, right? See, because when induction you go somehow towards the next value. Now you're saying the next value is obtained from the previous, right? It's better therefore to subtract, right? In induction, you go kind of upwards. In recursion, you kind of downwards. That's why we write n minus 1. But it is the same thing. It's just a different perspective that we take. And plus 3 was the condition. And this is now we have to be a bit careful here because we have to remain in the range. This is for n at least 1, right? Because I'm going to subtract, in this subtraction here, I have to make sure that I am within my range, that I have not gone beyond my natural numbers, right? Or even beyond the numbers where I know what f0 is. So this is a little bit, you have to be careful here, so that's why we start from n equals 1 here. Okay, so what is f of 4? Well, the problem hasn't changed. The notation is changed slightly, but the problem is the same. Okay, what is that? Well, it says you take the previous number, that is f3, you multiply with 2 and add 3 to that result. Okay, but we don't know what f3 is. Well, okay, what is f3? So this is what I was trying to say about the backwards working. We're going downwards. What is f3? Well, it is the previous one twice and then add 3 to it. Damn it, I don't know what f2 is, so I have to calculate f2 now. Okay, that is 2 times f1 plus 3. The previous one twice plus 3. Eh? This is, if you want, this is an instruction. At any given time, this tells you what to do. Okay, so I'm keep going. So I don't know what f1 is, right? The only thing I know is f0. It's clear that I need to know at some point something, otherwise I'm keep going down, 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 without getting anywhere. So f1 is 2 times f0 plus 3. f1 is twice the previous one, which is 0, f of 0 plus 3. Now f of 0 is 3. Okay, so let me perhaps make this with a color. So I'm using this here, and now I can plug this in, and I get this is 2 times 3 plus 3, so that is 9. Okay, now once I have this, I can work my way up. So the recursion is kind of down and then going up again. So from 9, because I can plug that in here, right? Because now I know what f1 is. So this is 2 times 9 plus 3, that is 21. Okay, this allows me to solve the next one here, f2. I now know what f2 is, that is 21. So this is 2 times 21 plus 3, that is 42 plus 3, that is 45. Okay, and finally, this is f3, right? So now I know what f3 is. This is f3, so that's 45. So I can plug that in here, and I get 2 times 45 plus 3, that is 93. So I finally found value of 4. So you see, why is this so powerful? Look, the number of calculations I had to do. I needed to do 4 downwards and 4 upwards, so about 8 calculations to find the value of 4. You say that's not efficient. No, that's not efficient. But what is efficient? That is, I did this with one line. One line made me wrote down a program that is basically 8 steps long. That is the power. A recursion is a very compact way of putting together a number of calculations, many calculations. Okay. Okay. So let me do another example, perhaps. Let's see what I want to do here. Yeah, let me show you where things can go wrong, where we have to be careful. Well, first of all, it doesn't have to be, we're now going to be a bit more flexible, okay? As in strong induction, we don't need to go, it's not going from a value to the next value, but it's going from all previous values to the next value. In other words, right? So if we now think the perspective of looking downwards, what does it mean? If I'm trying to find a function at the value n, I don't need necessarily to go to the previous number. I could go to the second previous number or the third previous number, or perhaps all of them. Not all of them, but a couple of those. So a valid, so here's another recursive definition. Take this one here. So the basis step, I'm going to say something about the basis step afterwards. But let me first write down the recursive step. This is as if you want the meat of the function. This is where everything happens, right? And the function, this is the relation. F of n, if you want to calculate the value at n, then you have to take twice the previous one plus the one before that. So this function depends not on the previous value, but it depends on the two previous values. Okay? And so could even have the three previous or the four previous. So this is general recursion. Okay? But now let's think about this. If I need, let's say, let's start with f2. If I want to calculate f2, what I need for f2, so n is 2, well then this is at 1 and this is 0, right? Now, it's clear that I have to start from 2 because I'm subtracting 1 and 2. If I subtract 1, if I take n equals 1, okay, that's 0, but then this is negative 1. That's not supposed to be, right? We don't have negative ranges here. So I have to start from n equals 2. So this has to be from n at least 2. Otherwise, I'm outside my range here. That's the problem, okay? But is this now well defined? So this is a question of well-definedness. Let's think about what happens. Okay. What I need to be sure is now that I'd be able to retrieve everything from these. I should be able to calculate whatever value. So if n is 2, go back to this case, just the very first calculation, right? F of 2, what is that? Well, n is 2. So this involves f of 1 and f of 0. So these two numbers I need to know. If I don't know these numbers, the formula doesn't apply anymore because n has to be at least 2. So that's the basic step here will contain in f0, gives f0 a value, I took it equal to 1, and give f1 a value, give it equal to negative 1. Okay. It could be negative numbers, right? So I just want to show you, it could be a negative number here. So, this is now well defined, because now in principle I can calculate any value. Let's do this again. This is not an efficient way of calculating the function, and we later on will do better. Okay, but for now, let's just do it manually, so to speak. F4. Well, the first thing is to understand really what the formula says. F4 says you need to calculate F4 using 4 minus 1 and 4 minus 2. Okay, so this would be 2 times F3 plus F2. But we don't know either one, so we have to calculate both of them. F3 is 2 times the previous one plus the one even before that. F1 I have, but I don't have F2, so let's calculate F2 first. Let's calculate everything until then we can start plugging back in. F of 2, that is 2 times f of 1 plus f of 2 minus 2, that is 0. Now this is the first one where I have full information, right? So here I have these two values, I can plug them in here, and so this gives me twice 1 minus 1, so that is, oh no, the other way around, sorry, I wrote it wrong. 2 times 1 is negative 1, right? Plus 1. So I get negative 2 plus 1, that is negative 1. Okay. Can I now do F3? Well, F2 I just calculated, so F2 can go, replaces this one, right? So this is the value now that I have. What about F1? Well, that's given, okay? So let's do this in another color here. So we have this guy now, that I'm going to put in here, and then I also know what F1 is, that this again comes from there. So we get 2 times F2, that is this value, minus 1, plus F1, that is negative 1. So we get negative 2 plus negative 1, negative 3. Okay. This gives me F3. So F3 I have here, that is F3. And what about F2? F2 I have 2, that was the purple guy. F2 is this guy. Hey, that's supposed to be purple. Okay. So we plug both of these in here. I hope I don't need to do this with too much colors, otherwise we're going to get seasick. Okay, 2 times F3, so 2 times minus 3, right? This value here, F3, minus 3, and then F2, that is negative 1. So plus negative 1. So this minus 6 plus 1 is minus 7. Okay, so now we can calculate even F5, right? F5, let's just for the fun calculate F5. F5 would be 2 times F4 plus F2, plus F3, right? It's from 5 you take the previous one, that's a 4, and the one before, that's 3. So 2f4 plus f3, and that would be, f4 was negative 7, f3 was negative 3, so this would be minus 10. And we can keep going and find a formula for that. Well, now I said something that I said it a little bit too quickly, and we can define the formula for that. That's not going to be that easy, and we're going to discuss that in a later chapter. Okay? So how to find actually a formula for this thing for recursive function? Many recursive functions can be written down with a formula, which of course is also very compact, but it's sometimes much harder to find those formulas. Whereas the recursive definition is extremely simple to give. Now, I want to do a couple of things about this, so 2 more things that I want to say, and then we'll stop. As I said, there's much more in this chapter here, but we're not going to do that. Let's look at this guy here. Okay, yeah. This one here. Fn is defined to be 3 times f minus 2 plus 2, and I also tell you that f0 is 1. Okay, so let's calculate f4. Notice what happens here is that it only to calculate the value for n, we need to only value the previous second, the 2 below that. Okay, we don't need the previous one, we need the one before that. So that's possible too. Recursion is very flexible in that sense. Okay, so what is f4? Well, that is 3 times f2 plus 2, right? You do according to this formula, you take from 4, you subtract 2, that's 2, and then take 3 times that plus 2. Okay, so that is then, what is f2? Oh, what is f2? I don't know what f2 is, so that is 3 times, subtract 2 again, so go 2 back, that is 0, plus 2. And I know what that is 1, so that is 3 plus 2, so this is 5. And therefore, if this is 5, then this is 3 times 15 plus 2, that is, 3 times 5, was already calculating it, plus this is 15 plus, is 17, right? So f4 is 17. Okay, so this function is well defined. What is f5? Let's figure out what f5 is. f5 is 3 times f3, go 2 back, right? Plus 2. You're following that? Okay. So what is f3 then? Well, now this will, on what it will depend on f1, right? So you can stop and try to figure it out yourself. Right? f1 plus 2. And then f1. Well, I cannot subtract 2 anymore because then I'm in negative values and it's not supposed to be there. So, okay. I cannot calculate f1. I have not enough information. So this is a bit strange, right? So I had this one condition here, and you had one basic condition. So this was the basic step, and this was the induction, the recursive step. But we didn't have enough information. The basic step was not sufficient. So this is what we call not well defined. So not well defined function. Because it doesn't give me every value that I want. Okay, and so what is necessary here is to make it well defined, to make it green. So to make it defined, I have to add a value for 1. What value? It doesn't matter, something. But as long as I have a value for 1, then I can calculate f3 and therefore f5. Yeah, you might say, yeah, but perhaps the next problem is then you keep running into problems. No, I won't run into problems anymore, because if you think about what happens, if I start from an even number and I go down by 2's, where will I end up after many, many steps? Each time I subtract 2, I will end up at 0. And that's, in other words, I will have I have reached a basis, the foundations, and from there I can work my way back up. And if I start from an odd number, if I keep subtracting 2, like 5, and then 2 subtracting 3, and from that you subtract 2, I will now end up at 1, right? So this is because 1 is the residue mod 5. Mod 1 is a residue mod 2, okay? So, and I also have f1, okay? So you have to be careful when you write down yourself. Now, you can trust that when they ask questions, you will always have a well-defined one, although in the homeworks it actually asks you to check this, whether they're well-defined or not. Okay, so, but I want to do now one more thing, because somehow, I don't know whether you're very satisfied with this, right? Because it's kind of, yeah, messing around and calculating things. Let's look at an example here. I want to do, where's my example that I want to do? Okay, this example, let's do this one here. So again, a new definition, new f. So the basic step is, I'm going to tell you what f0 is. f0 is 1. I'll take small values. It doesn't have to be 0 and 1 or something. It could be 513 or something, right? And then the recursive step, but I want to keep my numbers small. The recursive step is f of n is 2 times f of n minus 1, the previous one, plus 1. And this, of course, for n's that are at least 1, because I cannot subtract 1 from 0, so I have to start from 1. But this is now well defined, right? So yeah, this is what I should have also been more clear here. When is this, for which n is this defined? For n at least 2, right? Because I'm subtracting 2, right? And so there you see already the problem. Why is this therefore the original, without the green, the black one? Why was it ill-defined? Well, it tells you what to do for all n at least 2. It also tells you what it is for n equals 0, but it doesn't tell you what it is for n equals 1. That's why it was not well defined. Sometimes people say ill-defined. Okay? So if I say a recursive definition for n at least 2, then I have to give the values for every number that is not in this range. So then I have to give it for every number that's not in this range, and in other words, I have to give it for 0 and for 1. Okay? So here it's okay, because my n has to be at least 1, so the only thing that are not in this range are 0, and I am giving it to you. So it should work. Okay, let's work out one more time some of the examples here. So let's do f4 one more time. I know it's a bit tedious, but let's just do it. It's 2 times f3. Please stop the movie, try to figure it out yourself, right? 3 plus 1, f3. F3 is 2 times f2 plus 1, f2 is 2 times f1 plus 1, f1 is 2 times f0 plus 1. Now that one I know, that is, I'm using this here, that is 2 plus 1, that is 3. Sorry, 3. Okay, what's this value now? Well, now I can use this 3 and replace it by this, so that's 2 times 3 plus 1, that is 7. Okay, I can use that to plug it in there. That's f2, I know now what that is 2 times 7 plus 1, that is 15. And then I can use this and plug it in here, and I get that is 2 times 15, 30 plus 1 is 31. Okay. So now you might be asked, okay, so fine, you give this recursive definition, but I don't want to do it. Suppose you ask me f100. I have to do 100 calculations downwards and then 100 calculations upwards. That's way too much calculating. By the way, that's how a computer would do it, and computers can be very fast on this thing, so they don't care. Right? This is why this is very good for programming, because it's easy for computers to do this thing. It's basically do loops, right? Okay. So, so what to do here? Well, the thing is there are, in many cases, formulas. Now, how to find a formula? This is something, as I said, we will discuss. I think it's chapter 7. But for now, we're going to do, and the homeworks will ask you to do this too, is a bit of trial and error. Try to find a formula for this. That is not so easy. In other words, it's a kind of EQ type of question. What would be the next value be? Now, of course, we can calculate the next value, but just looking at a pattern. Can we see a pattern here? 3, 7, 15, 31. Don't forget the first number was 1. Now they're all odd numbers, but that's not helping much, right? It's not, they don't go up nicely. It's not a arithmetic progression, it's not a geometric progression, if you still remember what that is. Well, it's the geometric progression, we are very close here. Okay, I'm gonna kind of spoil it a little bit and kind of, what I'm gonna do is, look, I'm gonna say, compare these numbers that we just calculated with the following numbers. 4, 8, 16, 32. What I did? I just added 1 to it, all right? But these numbers, they have a nice pattern. They are geometric series, right? Remember, the geometric series is where the previous one is obtained from the next one by a certain factor, multiplying a certain factor. Here the factor is 2, okay? So what does this mean here? 4, what is that? That is 2 to the power 2. And this is 2 to the power 3. And this is 2 to the power 4. And this is 2 to the power 5. Okay? Let's see whether this was a good observation. So let's just calculate F5. Just double checking. Okay, I'll do it in purple. Double checking. F5. According to my formula, that should be 2 times F4 plus 1. That is 2 times 31 plus 1. That is 62, 63. Ah, yeah, 64. 1 higher. That is 2 to the 6th. Okay. So that's one thing. If I add 1 to my function, I get a power of 2. Which power of 2? What is the relationship between the function and the powers that we get? Well, let's look at the exponents. What are the exponents here? Well, let me first point them. 2, 3, 4, 5, 6. 2 corresponds to the value 1. 3 to the count 2. The fourth exponent corresponds to 3. So it seems that the exponent is always 1 higher than this. So what I'm saying is that if I take 2 to the n plus 1, 1 higher exponent, then I get these guys. Now remember, these numbers were, how do I get them? I added 1 to these numbers. In other words, if I want to get back to these numbers, I should subtract 1 from that, right? So subtract 1. So this is now my claim. I'm guessing that the function value, that the function is given by this nice formula, 2n plus 1 minus 1. Okay, is that the case? So now we're going to prove by induction. Once I have a formula, I can use induction or strong induction, depending a little bit. So let me say prove by strong induction. Why strong induction? Well, this case, induction will work. So I'm going to put it between parentheses. We'll do induction in this one. But sometimes you need strong induction because you need to go to previous values, not just not the single previous one. Induction is one step at a time. Strong induction is you can go down as much as you want or many times you want, right? That's the difference. Okay, so if you want to prove formulas for things like this, you're going to need strong induction. But for regular things, induction works. So how does the proof by induction work? So basic step is F0 is that equal to 2 to the 0 plus 1 minus 1. Remember, we have to prove this. Now, what is F0? F0 is given to us, right? I want to remind you, this is a given fact. So I know what this is. This is 1. Now, what is this value? 2 to the power 1 minus 1, that is 1. So this checks. Now, the induction step. And because I'm doing recursion, I'm going to do from n minus 1, so assume Pn minus 1 to prove Pn. I know that's not how we set up induction in general, but it's the same idea, right? I'm going from the previous to the next. Okay? So we assume Pn minus 1. And then we have to calculate Pn. We have to prove. So Pn is this statement, right? So Pn is the statement that this is equal. Okay? I'll put a question mark, but that's the statement. Okay. So Pn, what I have to do? I have to show that Fn is equal to 2n plus 1 minus 1. Now what is Fn? I'm now going to use my recursion. So let's write this with the recursion here. I have my recursive definition here. And that allows me to rewrite this Fn here. Remember, we always work with one side. We're trying to prove that one side is equal to the other side. We normally work with the left-hand side in these cases, right? So Fn is 2 times Fn minus 1 plus 1, right? That is what the prescription, if you want, of this function is. Okay. But Pn minus 1 works. What does that mean? I know that f of n minus 1, this function, is equal to what? The formula says, add 1 to exponent, take 2 to the n plus 1. So this is 2 to the n minus 1 plus 1. Right? And then subtract 1 from it. So that is a formula that assuming this, I know I can use this. So I can plug this in here. So this is equal to 2 times 2 to the n 2 to the n minus 1 plus 1. Now we have to work this out. That is 2 times 2 to the n, that is 2 to the adding exponents, right? Multiplying is adding n minus 1, minus 2 plus 1, that is 2 to the n plus 1 minus 1. Is this what I need to prove it is equal to? Yep. Okay, so the conclusion is this, and now I'm going to stop and let you do the homework problems. With a recursive definition, if it's well defined, you can calculate the values, small values, by going down and then upwards. But that can be a nuisance, and so sometimes you're going to try to find out, guess what the formula is. It's not going to be so easy, because I think the homework problems are supposed to be kind of easy guesses that you can do, that you can try to find. But if you cannot, okay, let it be then. I'll give you the homework solutions. So once you guess the formula, you should make sure that you use the right formula. So double check it really for at least 4 or 5 values that they give exactly the right thing. Then you can start trying to prove it, and then the proof is by induction. Why is induction work? Because recursion is exactly an inductive definition, okay? And you need induction. You can use regular induction when it's let's say the basic recursion, when you go from one value to the previous value. But if you do an induction involving more than one value, or perhaps even a value going back more than one step, you need strong induction, because strong induction allows you to pull information not just from the previous one, but from all previous ones. That's the difference between strong induction and regular induction. So strong induction, of course, can always be used here. If you don't want to think too much about it, you can always work with strong induction here. Okay, I'll leave it to the homework problems and see where far you get with this. Okay, and then we'll solve this more.